So folks, in this video what we want to do is build our understanding of center of mass. The first thing you'll need to do is make sure that you watch this video right here, which introduces the idea of center of mass. And then the second video here, which shows kind of an interesting problem of finding the center of mass of a broom handle. So click that link or that link there to see that. If you haven't done this, please pause this video or stop this video and go watch those two prior. So our goals for this section is to learn how to evaluate integrals for calculating the centers of mass. And to do that, we'll have to calculate both mass, moments, and then we'll combine those two together to give the center of mass in both 1, 2, and 3 dimensions. In this pre-work, we'll be focusing on the 1D case. So here's this first problem that we want to look at, and we're going to begin with this discrete problem. And so what we imagine is two point-wise masses here, mass 1 and mass 2. They are each a different distance from the origin, which is just the x-coordinate 0, and our goal is to find the center of mass across these two masses. This is not going to be a typical problem that we do, these discrete problems. Instead, we'll be interested in the continuous case, but by working this discrete problem, we'll begin to develop an intuition for how we want to tackle the more challenging questions. The first thing I want to do is give some notation. So we're going to use this notation right here, x bar. So this is red. X bar, which denotes the center of mass in the x direction, or for the x coordinate. So let's say that. And without getting too much into the weeds with details here, in those videos you should have understood that in those first two videos we should have noticed that the idea of center of mass would be like thinking of finding a balancing point where you could balance this system. So if you were to imagine here, which we don't have, a rod that's connecting these two masses, but you imagine that rod to be, say, infinitely thin and having no mass, then the question would be, where could you put your finger, just like you saw in the video, so that this entire system would balance? And that location in this 1D case will be the x-coordinate of the center of mass, x bar. And so we want to learn how to compute that. So the perspective that I want to take for this is sort of fudge the problem, and even though these two masses live in one dimension, they live on the x-axis, on the x number line, I want you to imagine that I have the ability for this entire system to rotate, in and out of the x-axis. And then if we think of it that way, when we do allow for rotation, we can talk about maybe balancing the torques created by these two masses at a single point. So what we want is we want some torque due to mass 1 to be equal to some torque due to mass 2. So folks, this takes us way back to where we talked about torque, and if you recall, we said that torque was the cross product of our lever arm vector times the force applied to the far end of that lever arm vector. So we get R1 cross F1, and that needs to be equal to R2 cross F2. Now, the forces on this will be fixed. What will change will be the R1 and R2, and we're going to have to figure out what those vectors need to be so that we can compute this center of mass right here. So again, let me say it like this. We've got on the right here, we've got mass 1, and let's just suppose we already know that that's where our center of mass is. Then there would be a force being applied to this lever arm. So this would be my lever arm right here, R1, and there'd be a force being applied to that in this direction here. So that force would be M1G, that's the force due to gravity. And here I'm going to think about this as living in the xy plane. So I would write this vector as 0, comma, minus M1G, and then because I need to take a cross product, I need to introduce a third dimension there. We put a 0 for the z coordinate there. Okay. Likewise, over here, maybe it turns out that this mass is more massive, so this vector is a larger vector here, this force vector, because this mass is, there's more of this mass. But we are computing the center of mass, so we want the cross product of this force vector right here, that's my force 2 vector, times this radius 2 vector. We want the torque generated by that to be equal to this torque over here. So if we were to come up with this force 2 vector, this force 2 vector would look like 0, comma, minus m2g, comma, and then we need to put it in R3, so we just add a third dimension there, calling it 0, so that we can actually compute the cross product. Now what we don't know is what R1 and R2 are in this case. So notice that if we were to think of these as vectors living in R3, that this would be some d1, and d1 is going to correspond to this distance right here, d1, comma, 0, comma, 0, because the vector just lives along the x-axis there. Okay. And here we have this other vector, and we could think of it as if we call this distance right here d2, then we could think of this as a vector d2, comma, 0, comma, 0, where I'm being kind of careless, not worrying about the signs just yet, because I'll take care of that in just a moment here. So if we set this up, we've got d1, comma, 0, comma, 0 is going to be crossed with this force vector right here, 0, comma, minus m2g, comma, 0, and we want that to be equal to a similar product on the right. So we'd have our d2, comma, 0, comma, 0 crossed with 0, comma, minus m2 g, comma, 0. And so if we were to perform that cross product, what we'd end up with is 0, comma, 0, comma, minus d1 m2g needs to equal the vector 0, comma, 0, comma, minus d2 m2g. And of course, two vectors are only equal if their coordinates are equal. So we get minus d1 m1g needs to equal minus d2 m2g. And if we were to just do a little bit of simplification here, dividing both sides by g, which are common between them, and multiplying both sides by -1, we end up with m1 d1 needs to equal m2 d2. And now what we can do is we can start solving for the center of mass, because the masses are fixed, m1 and m2 are. What we're allowing to vary are d1 and d2. If we're calling the hypothetical center of mass x bar, then d1 is the distance between the center of mass here and the location of mass 1. Because mass 1, as I've drawn this image, is to the right of x bar, I'm going to say that d1 would be x1 minus x bar, where I'm saying that this is at the coordinate x1. And on the right-hand side, we've got m2, and now we're going to talk about the distance between mass 2 and the center of mass. Well, if I call the coordinate for mass 2 x2, then this distance right here, if I want to ensure that it has the appropriate sign, this distance right here would be x bar minus x2. Okay. Now, if that issue of getting the appropriate sign is bothering you right now, as we work through this, we will come up with a more generalized statement after we've worked through this, where we don't need to worry about thinking about, wait, where is x bar in relation to these other point masses? But for right now, that's how we're setting it up. That made me not have to be quite so careful about labeling d1 and d2 in the original problem. So then if we take this formula right here, or this expression right here, we want to solve for x bar. So let's go ahead and do so. Distributing the masses, we get m1 x1 minus m1 x bar needs to equal m2 x bar minus m2 x2. And if we collect all of the x bar terms over to one side, I guess in this case let's take them to the right, we'd have m1 x bar plus m2 x bar, and if we take all the non-x bar terms over to the other side, we'd have m1 x1 plus m2 x2. Then I can go ahead and solve for x bar by factoring the x bar out on the right-hand side, so that gives me m1 plus m2 in quantity times x bar equals m1 x1 plus m2 x2. And so what we end up with is that x bar is equal to m1 x1 plus m2 x2 divided by m1 plus m2. Whew. That was tedious. But let's look at what we've just said here. If we want to find the x-coordinate of the center of mass, we can do so by taking this expression in the numerator and dividing it by what? Well, what do I have in the denominator? I have m1 plus m2. How could I think about that? I could think about that as the total mass of the system. Now, more complicated, notice up above here, what I have is each mass in the system multiplied by its x-coordinate in relation to the origin, 0 there. So we've got m1x1 plus m2x2. We give this a name. We're going to call it, in this case, the total moment. Although when we move to 2 and 3 dimensions, we will refer to that as we would refer to this as the maybe the y moment or the yz moment or something like that. But for right now, because we're just doing this for one dimension, we refer to the entire numerator as the total moment. Now, the thing that I want you to take from that is that in the total moment, in computing the total moment up here, I take each point mass and multiply it by x, its x1 or x2 coordinate, the coordinate from the coordinates for those masses. All right. That's actually going to give us an insight for how we're going to now do this in the continuous case.